My name is Kenan Boz. I'm the technical manager of EPMA, and I'll be moderating this seminar. As you may already know, SAM is an EU-funded project with the target of developing a sector skills strategy in additive manufacturing. Additive manufacturing, or more commonly known as 3D printing, is one of the key enabling industries for sustainable economic growth that is being widely used in a wide range of industrial applications. The AM industry has continued to grow over the last 10 years after a decline in 2009 due to global crisis in 2008. The average annual growth rate of worldwide revenues produced by all products and services over the past 30 years in AM is 26.7%, where the growth within the 4 years from 2016 to 2019 is more than 23%. At the same time, the world GDP growth average for the same period of 4 years was 3.4%. So I think this describes the huge interest or fast growth in AM. According to the Wohlers report, the total AM industry achieved a size of 11 billion euros by the end of 2019. As a result of such a high-speed growth, the demand for qualified labor force in AM has been an urgent necessity, which eventually called the SAM project to bring in a solution. So, to stay updated on the development of the sector skills strategy and the AM world in general, please follow the SAM project activities through our website of project, our Twitter, Facebook, and LinkedIn, as well as the AM Observatory as the one-stop shop for all the latest news on the AM world that you can also reach from the project website skillsforam.eu. You can also join SAM project working groups as an associated partner or an expert. We would welcome that. The link will be mentioned in the slide. I think Alexandra will also put it in the chat. So you can use this link to learn how to become either an associated partner or an expert in SAM project. In today's webinar, we will focus on the skill 3D thinking with the wider framework of digital skills. We will show some results of the SAM project and at the same time explore the topic from the different perspectives of industry, academia, and training experts. I would like to encourage you to type your questions in the chat. I will collect them and eventually submit them to the speakers during the Q&A session. So now I would like to start with my first speaker. This is Dr. Eujin P. From Brunel University of London. He is the Director of Postgraduate Research as well as the Bachelor of Science Product Design Engineering at Brunel. Dr. P will give a presentation with the topic of 3D thinking and design for additive manufacturing. So if you are available, can you turn on your camera, Eujin, and turn on your microphone?
Right, thank you so much, Kenan. Well, very pleased to see all of you. Such a lovely morning in here. So what I'll do obviously is to share my screen, and I hope you enjoy my presentation. Right, can you confirm you can see my screen?
Yes, we can see it. You can go on.
That's great, right. Okay, so I've got a session that I'd like to share with you, and the topic for today is about 3D thinking and design for additive manufacturing. So obviously, just to warm up, what I'll do is to introduce the university, introduce myself a little bit more, and then we go deeper into the topic about 3D thinking and design for manufacturing. If you've got any questions, just feel free to type it in the chat box, and I'll be very happy to respond. I'll try to make this session interactive, so again, we try to include some polls in here. Right, so again, this is coming from the SAM project, Sector Skills Strategy in Additive Manufacturing. We have more webinars, and I hope you probably continue to join us. So let's look at the next slide. So in this slide, it shows a kind of what we call a pretty picture, a very inspiring picture of the university. And within Brunel, what we have would be several complexes. Obviously, where you move along would be the Eastern Gateway, the main administration complex, followed by the main buildings, student accommodation, sports facilities, and further down we have more of the teaching complexes as well as for research laboratories. So within Brunel, we are about have about 13,000 students in total. Say we are fairly medium-sized university based in the UK, in London in particular, and we have about 1,000 academic staff, and we have in total 3 teaching colleges as well as 3 specialist research institutes which focus on different areas of research. So let's look into the research subjects. So we have 3 different types of areas of research, and in particular, we try to ensure that the research is impactful, it's beneficial to society, to the public, and also we try to come up with research solutions or creative solutions that bring value not just to the country but to EU and to the greater community. So we mentioned about the research institutes. We have the Institute of Environment, Health and Societies. And the second would be the Institute of Energy Futures. They look into energy modeling, they look into data, they look into sustainability. And the last one would be the Institute of Materials Manufacturing, which I'm a member of. So I am a member of the Institute of Materials Manufacturing. We very much look into material characterization, not just polymers, but also metals and composites. And in terms of manufacturing and conventional manufacturing processes, as well as digital manufacturing, manufacturing modeling, Industry 4.0, as well as additive manufacturing, which I lead a research group. So that gives you an overview about the university. Obviously, to give you a proper talk about the university would take me about an hour, but this is a very condensed version about the university itself. We have a couple of projects in here, and there is a website, web link, so World Wide Web, brunel.ac.uk/research and /projects. You see the list of projects, some ongoing, some that have been completed, some are EU projects, some are national projects, some are international projects, commercial, etc., etc. So just feel free to have a look when you've got a time, and very much happy to be engaged with you for those projects. So giving you a little bit more background about myself, I've got a research focus as what Kenan says on design for additive manufacturing, as well as on 4D printing. I know today's talk is about 3D thinking, but I've got a little bit of research also in the area of 4D printing, which is quite novel, which is really emerging. It takes a step further by using smart materials for 4D printing. In my day-to-day job, I work in Brunel University as director for postgraduate research, as well as leading the product design engineering programs in the university. I'm involved in standardization. So in terms of standardization, I'm the convener, or call it a chair, for ISO TC261 Working Group 4, which is for data and design in ISO level, as well as chair for the British Standards Institute for BSI AMT8 for additive manufacturing. I'm also a chartered engineer and a chartered technological product designer. Also the editor-in-chief for the PIM journal, which is from Springer Nature. So it gives you a little bit background about me, about what I do at the moment. So let's look into the topic. So we'll spend about 5 minutes about the introduction, give you a little bit about the topic. So why design, and why design for additive manufacturing? One of the main benefits about design, it's not really just about saving material. It's not really about trying to design parts that are functional, but really if you have a purposeful, well-designed part, you'll find that you actually can make your not just business model, but the process more sustainable. It reduces waste. It also helps to make the process more environmentally friendly. As you can see in this picture, poorly designed parts very often has got a very bad consequence of having a lot of what we call the support materials that need to be removed. That causes a lot of time. That also takes a lot of material, which can be really avoided if we have a better understanding of design for additive manufacturing. And to do design for additive manufacturing, we need to think about 3-dimensional aspects of this. So to start off with, when you want to start up, it usually starts with a CAD model. And the CAD model is usually the starting point of your 3D thinking process. So what I usually tell my students is that creating a Cad model can come in different forms. Obviously, you can download your Cad files from Thingiverse, from a Cad library. You can do reverse engineering, but very much so if you are creating a Cad model from scratch, this would be the three main ways. One would be a solid modeling using a solid modeler. The second would be a surface modeling, and the last would be script-based modeling. Each of these obviously involves different use of software, different approaches, solid modeling approaches, surface modeling approaches where you can pinch and pull that surface, or using programming scripts for the last one in here. Once you have got that process, once you've got a 3D Cad model that's created, you have to save the file. Obviously, that means you kick off with that digital flow, that digital chain process. So from the Cad model, you would have to what we call slice it, to make sure that you have each layer being generated also in kind of a file format, STL or AMF file format. Or other file formats include 3MF, OBJ, IGS format as well in the slicing process, where you actually input the machine parameters, and then you will also have the toolpath, which is the last stage for the G code for the machine to read the additive manufacturing 3D printing process to kick off for the print. So this would be the digital chain, but really the 3D model is where your 3D thinking process has a lot of a domino effect in the whole process chain. So it's very important to think about design for additive manufacturing. We're talking about design for additive manufacturing. It's a very wide topic, and usually it's linked to the use and the understanding and application of design rules, design methods, or tools. Tools could be software, tools could be flowcharts and things like that, to ensure that you are able to achieve the functional performance and the product considerations in terms of manufacturability, reliability, and also cost using additive manufacturing processes. So you can see in this image here, design for additive manufacturing could be integrated hinge assemblies. You manufacture that component in this photograph here in one process. You don't have to assemble that. You don't have to put onto the production line and get somebody to install that hinge. No, it's an integrated process. It's a one-stop process, which helps you to take advantage of additive manufacturing. Another one here could be designed for additive manufacturing, where you want to include integrated assemblies, say ball bearings, or maybe you want to introduce lightweight features. You have maybe lattices in here to reduce the volume, the mass, and the weight and the material. That's about thinking for design for manufacturing, but you are also integrating the parts together. Or on the right hand side, you have a hydraulic manifold from Olaf Daigle. So that helps you to consolidate all the parts. That's also about design for additive manufacturing, which is another area in here. So again, design for additive manufacturing could also take into consideration about support structures, because of the interesting process where parts that are less than 45 degrees tend to drop. You need to have support mechanisms. You need to have either support structures supporting that. But if you design it in a way that's less than 45 degrees, then you may need to think about the design considerations. So this picture here from David Wilson tells you about self-supporting structures. The first will be not self-supporting, so you have the red color zones in here. Second would be the self-supporting, you don't need support structures. Okay, and the last one would be a smooth surface, which again you don't need a support structure. So think about the angle, and that's really about design for additive manufacturing, because if the angle is lower than 45 degrees, you need supports, and those supports have to be removed, which means that you take an extra step, and that's where material is also wasted. So 3D thinking is also interestingly linked to the process itself for additive manufacturing. We know that additive manufacturing involves 7 different types of manufacturing processes. Each of those processes may require you to think about being creative, also about the types of material being used as well. I've got a little bit of time with you today, so I just want to go a little bit quicker, quite mindful of time. So in terms of 3D thinking, considerations for additive manufacturing, I break it down into 3 areas. One would be about the rules and guidelines for additive manufacturing. Second would be about the process capabilities, and the last would be the type of material choice in relation to the functional properties that you need to achieve. Okay, let's look at the first one in here about design rules and guidelines. You can see that design rules and guidelines will also be linked to general rules and also process-specific rules. Okay, so let's touch on that shortly. But to give you an example, on the right-hand side, you can see an example of this beautiful historical tram. So this historical tram was actually a project that we did together with the Kitsch Tramway Museum back in 2014. Well, that must be about 11 years ago. Okay, so back then, um, the tram museum wanted us to completely reverse engineer that tram because obviously in the 1920s they only had technical blueprints. They didn't use any CAD software, and we had to reverse engineer that. And to reverse engineer an actual tram into a CAD model involves a bit of thinking because they wanted us to actually 3D print that tram later on. So you could see on the left hand side, we've actually modeled that from scratch. We had to actually visit the museum multiple times, and this project took us about 2 years to complete. So later on, you realize that when it comes to additive manufacturing, you have to think about the consideration in terms of the build size of the machine. And here we use wet photopolymerization, which is SLA, and the machine was only that small. So we had to break it up into different parts and to remodel that. But bearing in mind that some parts will be very thin, so you might have to actually intentionally make it thicker. Otherwise, you'll not just print out, it would be just too fine to print. And a second example is about process specific capabilities in terms of thinking about the minimum feature sizes and also the accuracy and the service finish. That's down to the additive manufacturing process that you're thinking about. So another project like share with you is the Clam Light, which we did in 2007. So this project in 2007, we have different types of features in the Clam Light. It's essentially a lamp that has a clamping mechanism at the bottom for you to attach onto any work table. And you could see on the left-hand side, when we designed this Clam Light system, we only had 3 components. The main body, which in the center would be a living hinge for you to fold it and clip it, which we have snap fits, one main component. The second would be the lamp itself, which is a complex fluorescent light. And the last one would be the clamping mechanism, which is the third part in here. So only 3 parts designed for additive manufacturing. But where the considerations come in would be the structural ribs to give it structural strength. You also need to think about the internal details on that, give you the surface smoothness where the parts will be manufactured from bottom up. Okay, so think about it. You want the top parts, the outside, to be smooth and without removing support structures from the top so that you get a very smooth outside surface finish. Well, Kenan, you know, if I'm a little bit out of time, just let me know, but I've got a couple more slides. So, okay. The last one would be on mechanical properties of material, right? So just to touch on that, we talk about standardization. As you know, some of my work also involves in standardization. There's a list of standardization documents out there in the World Wide Web. You can search for it. But here would be standard documents involving working group 4. It talks about design itself. You could see some of those standard documents about design decision support, design for processes, for example, powder bed fusion, for metal extrusion, design guidelines for direct energy deposition, for functionally graded additive manufacturing. There's a huge amount of resources out there for standards. We touch on just 2 very briefly. Okay, so the first one would be about requirements, guidelines, and recommendations 52910, and the second about specifically a process-specific design guide 52911-1, part 1, which is for metals. There is part 2 for polymers, but we don't have time today. So let's look at 52910, the first one, which gives you an overview, and this would be a highly recommended document that takes into consideration about what you have to bear in mind when it comes to additive manufacturing. It talks about specific processes and specific considerations. For example, binder jetting, you need to think about the infiltrant to give you that solidity, right? To make sure that the powders are being infused together. It also tells you about post-processing treatments, the type of binder, the powder selection. So process by process, it discusses that in 52910. It also tells you the advantages of design for additive manufacturing, such as part consolidation from 24 pieces into just one single part. For example, here from Olaf Zegel's work, you can see to give you some examples in here from 52910 about multi-part processes. And also for 5291-1, which is for laser-based powder bed fusion of metals, it talks about the process itself. It talks about the feature constraints. It talks about other considerations to the process. So again, it gives you examples of what to bear in mind if you're planning to use part of bit fusion of metals or in polymers for part 2. It gives you recommendations how you can change. For example, you could see wine there gives you a recommendation that if you have a teardrop shape hole, you don't need a support structure because the top part is slightly higher than 45 degrees. Whereas if you have got a circular feature, you probably need a support structure. So you can avoid that support structures if you have a teardrop shape cross section in the figure Y in detail in there. Great, some examples in here. Okay, I think my time is up. It's about 9:20. So I just want to thank you again and thank Kenan and Alexandra for giving me the opportunity to speak to you. I think I've got a couple of minutes for maybe Q&A later. But in summary, think about additive manufacturing as a way to support your 3D thinking. Think about the rules and guidelines. Think about the machine process or the manufacturing process, and also consider the type of materials that you plan to use when it comes to additive manufacturing. My name is Eujin, so thank you very much for the opportunity. I can see Kenan's here online. Right, thank you.
We thank you, Eujin, for this nice presentation. So I would like to ask our audience if they have any questions for Eujin. Or we can also conduct the questions at the end of all 3 presentations. But if you have any questions, you can ask them directly now in the chat. Okay, we're quite on time actually, but maybe we go on with our, sorry, okay. Okay, it's not the question. We go on maybe with our next presenter. That is Dr. Georg Schlick. Oh, 1 minute. So there is a question. So just wait, Eujin. That's always the case in online events. People get slowly used to asking questions. So the question is, let me check. What is your criteria for evaluating manufacturability?
That's an interesting question for Elias about criteria for manufacturing or evaluating manufacturability. I think there's a lot of criteria. It really depends on where you're coming from. Most of the time, if you're coming from a company's perspective, a business perspective, it's about cost, okay, and it also often results in a type of material. Material and manufacturing come hand in hand, access to the resources come hand in hand. It really depends. If you're talking about coming from business perspective, that's about cost. So that's the bare basic. But if you don't have anything, then I think when it comes to evaluating manufacturability, it could be in terms of surface finish. So potentially surface finish would be resultant in the type of maybe powder or the type of machine you have on hand. It really depends on the perspective. Okay.
Okay, another question from Rodolfo. He asks, what would be your suggestions for someone who is just starting with design of AM?
Okay, I think for Rodolfo's question is really interesting about someone starting from the FEA. I would suggest reading as much as possible, right? Reading not just standardization documents as possible, but in terms of understanding the processes, understanding some case studies, how people go through that process, but also really experimenting it. You'll realize that design for additive manufacturing a lot really relies on your experience, trying out different ways. You find that, that kind of machine can only achieve that thickness, or that kind of machine can only produce those parts with that kind of precision, then you understand the parameters and the constraints. You become much more confident. Reading as much as possible and trying out as much as possible. Practice and theory becomes important if you're starting up for the FEM. So that would be a good starting point. Or enroll in some of the courses. I think, if I'm not wrong, we plan to have potentially maybe in the future some courses about design for additive manufacturing as well. Thank you.
Okay, thank you. There's not question, but a comment from Daniel. It says, I'd recommend getting a cheap fused filament printer with a price of £300 and try it at home in spare time. Maybe that can be a solution.
Good advice.
Okay, thank you. So as I said, we will go on with further questions at the end of the webinar. So now let's say thank you to Eujin and give the floor to Georg. Our next speaker is Dr. Georg Schlick from Fraunhofer IGCV in Augsburg, Germany. He's heading the Department of Additive Manufacturing, Materials Engineering, and Technical Cleanness at Fraunhofer. His speech will be on 3D thinking applied to a real working environment. That is, how does it affect the production and the use of the technology? So I already see that your presentation is on screen. Hello, Georg. So nice to see you here. So
Kian.
it's time to go on. The floor is yours. Thank you.
Yeah, thank you very much for actually having me here in this seminar on SAM. And yeah, I'll try to give an insight into 3D thinking applied to a real working environment, whatever this means. And I'm glad to be able to show you some of the results of my colleagues, Matthias Schneck, Matthias Schmidt, and Max Horn. So I would like to start to actually introduce my company for a moment. So who am I? I'm working at Fraunhofer IGCV, located in southern Germany, Bavaria, a city named Augsburg. And we are working in applied science on production engineering, actually. So what is it we are doing? We are working in the areas engineering, production, and multi-material solutions. And we are doing this along the whole production line, so to say. So we start with materials engineering, design methods, design, processing technologies. And last but not least, we're also organizing plants and factory setups. So that's where we are putting our scientific expertise. And in the first part, materials engineering, design methods, design and processing technologies, we're actually specialized on casting and composites. However, we have a very strong part also in additive manufacturing. So in casting, composites, and what we call production engineering, we have three branches or departments that are actually working a lot with additive manufacturing. This starts with additive manufacturing for sands and toolings in casting, and goes over to polymers and composites, and also especially reinforced composites, 3D printing of reinforced composites, which is focused at the department of Professor Iman Taha. And myself, I'm head of the department where where all the metal additive manufacturing is going on at Fraunhofer IGCV. So we have three research groups with 16 people all in all on additive manufacturing of metal and metal multi-materials, so combining different metals and combining metals with also other materials. So when talking about 3D thinking, I want to start with a more or less straightforward example. Optimizing a hydraulic block. This is an example you will see rather often in literature. You'll see that this is done sometimes, and so we started with okay, that's a drilled block with a lot of holes, and what do we do if we want to optimize a part like this? We really do know the boundary conditions. We do know where to actually place it in the towards the next part. So we have all the boundary conditions, and then we go in a, I would say, rather straightforward optimization loop. We have the pipes. We know where all the interfaces are. We may start with an easy design, and then we need to lay over the design thinking for additive manufacturing over it. So we get something that we can actually manufacture. We bring it to the machine and we manufacture it. And in terms of optimization, these hydraulic blocks are typically rather low-hanging fruit because you can always save a lot of weight, and you typically get a better performance because the joints and all the pipings, they will get much more smooth, and they don't have these hard cranks just around the corners after designing for additive manufacturing. But when you need to think a bit more out of the box, it is often very helpful to actually go away along biomimicry. So I brought you some certain analogies from nature, and I will apply them to actually a rather simple part in the next steps. But the idea in biomimicry is always to break down the problem, to see what do you actually have to optimize, which properties need to be optimized of the part. And then typically nature gives us a lot of examples where these things are already optimized. So well, one example can be the human bone here in this example, which just grows in a way that it can bear a lot of weight and has a lot of strength. But also some algae, and especially some plants like giant water lily, stalks and grasses, and also juncus, which are all plants. They have a certain structure within their leaves and stalks that can actually bear much more weight and also give some flexibility to the solution. So what I want to say is that often when we talk about optimization, we think also in simulation, but for many problems this is not as easy as one would think. And it can be really interesting to also see what can we come up with when we do product development with these biomimicry solutions. In the next slides, I will apply this to a rather straightforward solution. However, nature also brings us the opportunity to design to much more properties than typical simulation would be doing. So nature does also do a lot of fluid transport and strength. It's always combined with flexibility. We also have heat transport and cooling, and this is often not as easy as one would think to combine it in one simulation. So the application I brought to you is actually something rather simple, a gear wheel. Oh no, it's not that simple, but it's an example that everybody knows. And in gear wheels, typically there is one part not optimized at all, which is the connection between the teeth and the rod. This is very hard to manufacture, and it is not as easy to know how would you actually place or design this part in here. So what have we done here? We have taken a stalk, the so-called rough horsetail, which has a certain structure to be structurally strong, and we moved this to a design for a gear wheel, and then we did a simulation for safety factors around 1, and could do a mass improvement of approximately 30%. Very similar in terms of what we have done. We can also use a structure coming from an algae, which is the diatom, and we move the same structure to the gear wheel, and we come up with very similar values. So we have a safety factor of around 1, so the gear will still hold, and it will still be usable very, very well. That's what we already have tested as well. But we will still have mass savings of about 30%. And a third design we looked at is the Uncus, which is a plant, and this has a microstructure with a triangular shape, and the triangular shape applied to the gear wheel looks like this in this case, and we come up with similar values, and we get them more or less the highest mass improvements here. So when we take a short look, we can actually use the analogy from biomimicry to have a major mass improvement in the gear wheel, still keeping a relevant safety factor, and also keeping the displacement in range. So this could be more or less the second optimization factor, because this would actually leave us choosing the rough horsetail, which has the lowest displacement for this specific optimization. Or we could actually go for the Uncus, which has the largest mass improvement with similar boundary conditions. Now, this is an example where we could actually move to a very certain lightweight design using additive manufacturing and 3D thinking. And what I've not shown here, but what we could show also in the lab, we are getting very close to also regular simulation optimization by this manual approach in this case. So this can be a way to actually think in 3D and open the mind, go out of the box for 3D thinking, getting ideas from biomimicry. Now, I kind of want to jump to things that we are working a lot with, because here we see that this can open a vast new way or vast new opportunities for 3D additive manufacturing and also 3D thinking. Next step in design freedom from our point of view, or actually research is ongoing in this area, is 3D multi-material processing. So that's one of my own major research topics. And as you may know, with additive manufacturing, it's rather easy to combine two materials in a discrete material transition, also especially in one direction. However, what we're achieving, or what the actual research goals are going towards continuous material transitions on the one hand side, but onto 3D multi-material applications in the end. And for that, I brought 3 ideas that come from actual industry nowadays, where we have a combination of different materials. This is especially in e-mobility and for electrical motors. One tries to combine specific strength with high electrical conductivity. And so this is a conventionally manufactured part from aluminum with copper alloy. However, if we could go towards additive manufacturing, design possibilities will increase much more. Very or let's say similar idea would be dental implants, where we would like to combine a specific strength and biocompatibility with very good osseointegration. So we combine titanium alloy with tantalum, and also combined a very good flexible E-modulus, or Young's modulus of tantalum with a very strong titanium. And third part that is actually coming from our lab is where we are going towards die casting tools, where the plan is to increase thermal conductivity without always using or without losing too much material for cooling channels, and combine this with high strength, high hardness material, in this case a tool steel, to actually also improve functionality here in this area. So in the end, what I try to show you is, on the one hand side, that 3D thinking can be an interesting process, and it is a process that can actually be supported by biomimicry, by looking into the nature. And on the other hand, we are also technologically going towards one thing that Major does as well. It does also combine multiple materials in one part, or in one creature, so to say. But for the process of 3D thinking, multi-material processing will actually make these things even more demanding to get the very much optimized part, and to get everything out of your design. So I'm not sure how I'm in time. I think I was rather a bit quick, but thank you for your time. Thank you for listening, and I would be open to questions now or later.
Thank you, Georg, for this nice presentation, and it is interesting to see the variations regarding the material in 3D thinking and design of additive manufacturing. So, as Georg said, and I want to repeat once again, there are some questions. One is from Andy, I think. Hi, Andy. If you can unmute yourself, you can pose your question.
Thank you, Kenan. Thank you for your presentation, Georg. I just wanted to ask if there's any industrial applications of multi-material AM. There's any particular example you could single out that we could look into if we wanted to know a little bit more about that?
We've seen some applications, especially in tools. This can be die casting tools, like the one I've shown. Some of those are actually in use at manufacturing companies, which are doing different ways of die casting. But we've also seen this already in cutting tools. So especially in cutting tools, combining hard metals with high strength steel is something that is already going towards an industrial application as well.
Okay, so we have some questions on chat. Let me go one by one. The first one is from Rodolfo. Regarding 3D multimaterial, do you see a specific processing technology as an enabler, or should we think of combining different AM processes?
Very interesting question. Actually, well, we've shown that we can do multi-material in powder bed, which is the more demanding way in engineering for the machine, but allows us also to combine materials in the powder bed and have filigree structures using one of the mostly wide used additive manufacturing process. However, there is also two There are two processes that I see will be enabling the thing. As one on the one hand side, this would be laser powder bed. No, not powder bed fusion. This is directed energy deposition with laser and powder, and cold gas spraying. Because with cold gas spraying, we expect that we can combine much more different materials than we do with welding, with the welding-based additive manufacturing processes. And I think it's a good point. And for certain applications, we will definitely need to combine several processes into a hybrid process chamber or hybrid machine.
Okay, thank you. The next one is from Zhao. Could I ask that for the multi-material die, which technology you use to produce it?
Yeah, we actually use laser powder bed fusion. So this is produced by an experimental process we have set up in our lab. So we use powder bed. We have one material that we bring to the powder bed. We melt it, we take it off, and we bring a second material to the powder bed. That's the experimental setup we are working with right now. But we see several ways, and we're working on several ways to actually bring also two powders within the one powder bed.
Excuse me. Do you think we can use the direct laser deposition technology to produce such kind of die? Or
yes, I do think so. When thinking about larger structures, especially, this is also an opportunity one could use, or a possible way to achieve similar parts.
okay, thank you.
Okay, so next question is from Daniel. You spoke about the benefits of multi-material printing. Are there any commercially available systems for multi-material printing? Yeah, is it available on the market to buy a multi-material printing machine?
Actually, it's becoming available. That's what I would say. Some of the additive manufacturing equipment manufacturers are offering multi-material processes on a rather, let's say, experimental base. However, you can buy one machine by Econity together with Aerosint. So this would be powder bed fusion with two materials, and yeah. So it's becoming available. That would be the answer I would like to give here.
Okay, thank you. Next question is from Alirza. What is your idea about reducing the residual stress in multi-material 3D printing?
I would say not addressed that well yet. We haven't had too much problems with residual stress in multi-material processing compared to residual stresses in monomaterial processing. So the thing will still be doing the right thermal treatment after the process, which is actually a research topic on its own.
Yeah, we receive a lot of questions, Georg. I think your topic has been really under focus. So the next question is from Tuli. Hello, Tuli, by the way. She's asking, how much success did you have with powder fusion using materials of significantly different melting points? Good question. She also says, my question is more on in situ alloying.
Okay. Yeah, the special thing is with the very focused laser is actually that it is possible to combine materials with significantly different melting points. I think I have to. I think we have already combined aluminum with a copper alloy. So these things can actually work. And as I said, with a very focused laser beam, it's possible to melt almost all of the materials, and you can combine certainly materials with very different melting points.
Okay, thank you. Next question is from Mihail. Availability of multi-material. Oh no, that's a comment. He said he saw some parts some time ago. Oh yeah, it's getting more and more popular, by the way. As Georg, you may remember, our last year's AM seminar of EPMA was focusing on multi-materials, and there were really nice case studies. One was from Sweden, company named VBN. So it's getting more and more popular day by day. So thank you. I think that's all for Georg's side. But as I said, if you still have some questions, do not hesitate to put it on chat, because if we have time after the webinar, I will try to put these questions to our, ask these questions to our speakers as much as I can. Thank you, Georg, for this nice presentation once again.
Thank you very much.
Okay, so our third and last speaker is Dr. Alexander Hiricoiu. He is Senior Application Engineer at Ansys, specialized on the design and simulation for additive manufacturing and related training methodology. He will be speaking on design for additive manufacturing, challenges, critical skills, and effective training methods. Hello, Alexander. I already see that your presentation on screen. Thank you very much.
Thank you very much for inviting me.
Yeah.
Can you hear me well?
Yeah, it's all perfect. We hear you. We see your presentation. The floor is yours.
Perfect. Thank you very much. So good morning, everyone. And again, thank you to the whole SAM organization for giving me the opportunity to present during this event. The main topic I will try to cover is the design for additive manufacturing, highlighting the main challenges, critical skills, and also most efficient training methods we can adopt in order to make the technology, I would say, more available for the market and the industry. In today's presentation, I will then cover 4 different points, starting with a quick introduction to additive manufacturing, where I will try to highlight which are the biggest challenges today that one may facing when starting additive manufacturing. Then what are the skills required to overcome those hurdles in additive manufacturing, and how can the simulation help the 3D thinking through generative design or topology optimization, for example, as well as the modeling the process itself to understand better what's going on inside the printing machine. Last but not least, I will end my presentation by providing some guidelines for training and skill development for the people that are just starting with additive manufacturing and would like to ramp up their knowledge about the technology. As a short introduction, I think most of the people inside this call, they are very familiar with additive manufacturing, and the 2 previous speakers really gave a good overview of it. I just would like to remind that the name additive manufacturing is put in opposition with the more traditional subtractive manufacturing techniques. And as Dr. Pei said in the first presentation, one of the main goals for additive manufacturing, of course, would be to provide the designers the free of shape they wanted in when they are creating the new products, but also it aims to reduce waste during the production phase. And this has to be taken in consideration already from the design point, because if you are not careful about your design, then you end up generating supports and rubbish material that will not be let's say leading to this reduction of waste material that is in opposition with again the subtractive manufacturing. This slide kind of shows the landscape today for additive manufacturing, or at least for over the past 3 or 4 years. And what we see is that in terms of technology, there are 2 to 3 main technologies that are dominating the market. Those are vat polymerization, powder bed fusion, as well as material jetting. And of course, if you are aiming to get a job in the additive manufacturing industry or starting to design, you might want to focus really on those technologies, because those are the main technologies that are adopted in the industries today. And as it comes from the material side, then there are 2 big branches that are dominating nearly 90% of the market, the metals and the polymers. In today's presentation, I will mainly focus on the metal part of additive manufacturing. The reason being is that you can make the most of the simulation for the metals. You will face much more painful bad experience with metal printers if your printing fails than with polymers, which is I would say cheaper to work with. As some of typical application cases, we'll have first the prototyping, and that is well suited for additive manufacturing, simply because when you are starting to produce a new design, new concepts, you would like to test them without creating all the serial production tools that are required for the later stage. So you can really quickly evaluate a different design, test them, and then see if they make sense or not through the additive manufacturing technology. The second application that we see as a big trend in the industry is tooling. So basically, instead of producing your part, you are going to create through additive manufacturing the tools that are required to produce your parts. I'm thinking about molds, for example, for injection, pressure injection, casting, and other hot forming tools. And one of the key advantages is, of course, the free of shape that will help you to design, for example, the cooling channels to have conformal cooling all over your part. So through the additive manufacturing application, you are going to bring in very specific optimization of your part, and you're going to provide an added value to the traditional parts you add before using additive manufacturing. Last but not least is the serial production of part with very high value added, for example, lightweight or bionic shapes that could not be produced any other mean by just additive manufacturing. And there is now also a fourth emerging market that is the part on demand. So for example, for spare parts, it can be sometimes very expensive to store those parts for decades. So it would be much easier to simply produce the part when you need to replace, for example, into a nuclear power plant or somewhere where it cannot be easily obtained. Those advantages, I would say, they are kind of counterbalanced by some very big challenges that one needs to overcome when it starts with additive manufacturing. And the first of those challenges is related to the technology. When you are trying to adopt additive manufacturing, you will often see problems with the material. So you will need to evaluate your machine and try to set it in the way that it will produce a very good material, low porosity, and that is in alignment with the regulation that could be in your industry, for example, aeronautics or any other sector. Of course, you also need to think about the process implementation of additive manufacturing inside a company. If you buy a printer, you need to dedicate a room to this printer, and of course, you need to set everything in that room so that your powder, they do not get contaminated with external material, and also your people, they don't get contaminated with powder, because hygiene and safety is also very important within the field of this technology. Then, of course, there is the post-processing that is often required. It could be heat treatment, support removal, surface finishing, etc. And there is the control and the certification of your components once they are printed. Another big challenge is the shortage and lack of regulation or standardization for IM technology. I'm often thinking about all those different software that exist out there in the market that could not exchange data, and also the printers themselves. Each one is using a dedicated format, and you cannot take one file to another machine that is from another machine provider, for example. So this makes the adoption of technology a bit harder also, because if we are already equipped with some software, you cannot simply just switch from one company to another, or from one type of technology to another. there is a shortage of very skilled people, and those are not only designers, but could also be at the machine level, machine operators, technicians, and so on. And last but not least, for designers which have had past experience with more traditional and well-established process like metal forming, casting, it's very hard to start thinking for 3D printing process. I'm giving you an example here. You have this part there, very organic, that is in the simulation. If this part has to be a critical, mission critical component, it will be very hard for some people to trust this part because of its organic shape. They would like to see something more traditionally made with safety factors of about 5 to 10, right? So those are, I would say, some of the biggest challenges for the industry itself. I think if you are starting with a new technology, you are quite familiar with this representation. Additive manufacturing also comply with this. So what will happen is at the beginning, when you buy a printer or when you start with a printer, you will get you have very low maturity with this technology, but your expectations, they are going to grow every day, and those expectations, they are going to reach a peak when you are starting to have your first failures or multiple failures, and then you are going to lower your expectations, but through the failing phase, you are going to gain in experience and in maturity, and eventually, if you don't stop there, after a while you will reach the plateau level that will allow your productivity, and you will have less and less failures, and you are going to produce more components that are efficient for the market. To do this, the skills required for designers, they are, of course, I'm not breaking any ground here. If you want to be a good designer for additive manufacturing, the first skill you will need is a good knowledge about the CAD softwares that are out there on the market, right? Then you also need a very open mind to innovation and design for additive manufacturing. There are rules and you need to accept them. I think Dr. Pei at the beginning really highlighted some standards and guidelines that are set for additive manufacturing. You really need to accept those and move forward with this technology. Then you need a very good understanding of the post-processing required once a part is finished, because this way you can take this in consideration already from your design, and very good knowledge about the material themselves, how those materials can be produced, and how material tuning could affect the mechanical behavior of your components. The part on demand, for example, will require very good strengths in reverse engineering skills. So this will be the ability to clearly identify from your traditional products which are suited and well fitted for additive manufacturing, and which should remain in the traditional production line, because not all parts, they are made for additive manufacturing. And again, additive manufacturing, I don't think it's going to replace all the traditional manufacturing processes in the world. And last but not least, you need very good teamwork skills. This is mainly because when you're a designer, you are going to very closely interact with people on the production floor that will tell you if this part can fit inside the machine or it can be printed or not. And also with the simulation team that can eventually evaluate the printability of your design before moving into the printer, right? And with that being said, I would like to give you an example here that we did with one of our customers of very successful additive manufacturing, and this really addressed the reverse engineering part of it, analyzing which products are well suited for additive manufacturing in terms of efficiency as well as cost reduction. So this was one of our American customer. They are producing antenna components for satellites, and they had this antenna that was made of over 100 different parts, and they thought, why not using additive manufacturing and combine all the parts together in one single? And by doing so, they reduced the cost of development and production for those components about 75%. Of course, breaking the whole supply chain and assembly chain reduced tremendously the lead time of about 80%. And last but not least, because they could optimize this single component instead of having like over designed 100 parts, they could also make the part more efficient and save fuel for the rocket of nearly 100%. So they reduce by a factor of 2 the fuel saving, or the increase, sorry, the fuel saving. And in all of this, how can the simulation help you? Well, the simulation is there to assist you to understand your design, to help you clearly drag your cost down by not producing parts that will break during the fabrication process, as well as increasing repeatability and reliability. And the reliability is here a key factor that can really be evaluated through the simulation. This is, I would say, a chart that will provide some kind of guideline to virtual modeling. Of course, at the beginning, what you were going to do is based on some experimental evaluation, you are going to calibrate your model. You are going to put different physics inside your model and different parameters, and you are going to do it as long as your simulation will not fit the experimental data. Once you get a very good fitting in between the simulation and the data, then you are moving to the second stage, that is understand your design. And in there, you're going to run some DOE to see among the different physics you input inside your model, which one are dominating, let's say, the efficiency behavior of your part. Once you identify those key parameters, then you're going to move to design optimization or improvement by changing those parameters, looking for, like, for example, using gradient methods, looking for a global optimal functional point of your design. And once you're done, then you need to move to the last and most important stage is the robustness analysis, because, for example, if you use topology optimization to get a very good design, what will often happen is that if you don't plan for all the load case scenario, then your design might just break during the testing phase. So this is the role of the robustness insurance analysis, to make sure that your design will stand the life cycle no matter what. And here I pronounce some big words like topology optimization. This will lead me to talk a bit about what is now very famous on the market of optimization, also called generative design, or as we call it, or as we prefer to call it, design exploration. So this is a bit different of topology optimization, because generative design is, I think, a visual support for designers in order to help them understand how input parameters could affect their design. And in this case here, we have a simple geometry, and we run some kind of optimization over it, and we ask the software, what happen if so what happens if I set, for example, a constraint of max thickness for my design, and we see how this can change your original optimal form, right? What happens if instead of using this part for additive manufacturing, I want to do some kind of metal forming. So I would like a pull-out direction, and we see the third kind of design. So this is what we call design exploration, and it's to enable, through the simulation, designer to quickly assess how their design will behave under some specific rules that could be constraints on the fabrication process itself, or constraints and loads over the part or the design space they are going to create. The main role of topology optimization is to link the products, the people, and the process together. So first, the topology optimization will enable different kind of people that could be FE simulation experts or designers to really understand the behavior of that design, and then it will help them to improve already existing, I would say, components, or create designs for new type of processes, right? And with that, you have one of the most famous, I would say, simulation edit design tool that is called Topology Optimization. And in Topology Optimization, you will often start from a block, and you will ask the algorithm to optimize the part given you maybe the highest strengths, or using, for example, lattices to design local mechanical properties that will be kind of local material tuning in order to enhance the part capabilities, as well as reducing the weight of those components. Last but not least is the simulation of the process itself, to really understand how your part will behave once inside the printer. And at this point, I need to make clear that no matter what you are going to do before in the design, no matter what rules you are going to apply, you will still have problems once you go inside the printer. And for that, just look at this animation here. That is this propeller, right? It's quite symmetric. All the blades, they should see about the same distortion if it happens inside the printer. However, because of the scan strategy, in some areas the scan lengths, they are going to be shorter. In some other, they are going to be longer, and this will create different thermal conditions all over your components. So you will end up with hotspots like that. Will be the red areas locally in some areas, and this will create higher distortion than in some others. And if you don't assess this through simulation, it will be very hard to anticipate before going into printer, and even after, it will be very hard also to correct. With that being said, I just would like to highlight the Ansys solutions for additive manufacturing. So of course, we have tools for the designing part, like topology optimization tools, or more design exploration tools. But we have also the full chain in order to help people to understand how their part will behave inside the machine, and how to finely tune the machine parameters in order to achieve good material properties, I would say, in terms of porosity reduction and microstructural enhancements. Before finishing, I would like to take you through the last point, that is the training and the skill development. There are different methods out there, and I would recommend two of them. The first, they are specialized institutes that are offering hands-on classes that will help you to understand the theory of it, and also they will give you a practical application by allowing you to print your components. Of course, you will be assisted. I attended one of these classes 2 years ago in the Fraunhofer in Hanover, the Centrum Laser there, and it's very good for designers, because the last day you are going to take your component out of the machine, and you are going to be asked to remove the part from the base plate, cutting all the supports and so on, and you will see how difficult this is as a process. And later on, when you will think about designing something for additive manufacturing, you will think about that kind of challenges. The second method will be through e-learning, and Ansys as an all campus dedicated to e-learning. And we have one specific building in that campus that is really dedicated to structural engineering. And within the structural engineering, we have a room for additive manufacturing. There you will learn basic topology optimization skills, as well as process simulation. And you will be able to interact with some of our experts, as well as taking part in challenges that we often set, or the online classes that are also set on the e-learning hub. The same stands for the design building, where through our GPU-based tool, you will be able to explore designs in a couple of seconds. It's a very well tool for designers to not really go too deep into the finite element modeling, but still be able to run simulation through the discovery products. Before finishing, I would like to highlight the Ansys World Conference that is going to be held in April this year. You can register for free, and you will be able to attend keynote speeches about simulation for all the industries and most relevant challenges we have to face today. With that, I would like to thank you. And if you have any questions, please feel free to ask.
Thank you, Alexander. Yes, we have some questions. Actually, we have some other questions for the other guests, but let's start with your first questions first. So first one is from Joamin Gonzalez. For what AM processes are the process simulations available from Ansys?
Sorry, the DM processes. So basically, our main focus is powder bed fusion, but we have also tools for DED and biojetting.
Thank you. Next one is from Adriza. Is there any plan in Ansys to make the image-based simulation easier and reliable to be the parameter for manufacturability evaluation?
I'm not sure I understand fully this question. So I would say inside the workbench environment for Ansys, there is the possibility to set parameters along your design, and then once you do that, you can track down some output parameters like the residual stress or the maximal distortion on your component, and then through parametric optimization, for example, you can link the inputs to the outputs and automatically ask the software to change your design so that it reduces those criteria to a minimum possible. However, something that is not always possible is to completely cancel the distortion because of the thermal gradients on the components. So what we can also offer there, it's compensation for your components. So we are going to help designers to pre-distort their initial design in order to take in consideration the deviation or the distortion that will occur inside the machine while printing the components. I hope this answered the question. If not, please let me know.
Yes. Okay. Let's go with the next question for you, Alexander. How can we join the Ansys online training module of topology optimization?
It's very easy. You need to contact Ansys and join the Ansys Learning Hub. So if you go through Ansys portal, so ansys.com, you will have one section dedicated to training, and then you will be redirected to the Ansys Learning Hub, and you can subscribe for it. If you're an Ansys customer, please contact your local Ansys contact. They will provide you, I would say, logins for you to connect. If you are not, then you can certainly ask there to be put in contact with someone that will authorize you on the Ansys Learning Hub.
Okay, thank you. Now we are in a session of Q&A. You can also raise your hand and pose your question directly. That's possible. There is a missing question to Georg from Damian. If Georg, if you're available, I would like you to ask that question. Can you please explain how do you think to print multi-material electric motors? I couldn't understand the question exactly, but if Damian can unmute himself and put the question in a more clear way, that would be perfect. Or maybe Georg already understood and he will be able to answer. I don't know.
Actually, I think the question aims also towards the combination of materials with very unsimilar properties, because we are looking into that, and the very difficult thing on the electric motors is actually, first of all, combining materials with very different electrical and magnetic properties. So we need to combine much more than only metals with metals. We also need to combine an insulator that is, or an insulating material that can be processed in this in the same manufacturing machine, so to say. So this is one way where we are actually going back to another question we already heard because this may mean that we need to combine several additive manufacturing technologies within one build chamber or within one machine.
Okay, thank you. And as far as I know, Foucault currents is another problem in electrical motors. That's why you have the laminated structure that can be a obstacle. And what I know in electrical motors, the main focus is to produce magnetic materials that is called the functional materials, where you can have artificial magnets that would really speed up the performance, electromagnetic performance of the motor. So most of the better electrical vehicles companies are working on this subject of additive manufacturing, that is to produce artificial magnets in certain shapes, in high quantities, etc. Okay, so we have a question from Rico. It was a general question to all of our speakers. He says that we have heard about several different AM processes. When choosing the right AM process, is the first analysis done based on the design of the part or based on the required material properties? So who answers?
Please go ahead, guys. If I can give my opinion, first of all, I think to start designing something, you need to set your process in mind, because you'll not be designing with the same rules for polymers as for metals. And of course, you will not be designing with the same rules for aluminum alloy as you will design for Inconel or titanium. For example, we were talking before about the overhang angle. It can be much lower than 45 degrees for aluminum alloys if you correctly set the process parameters inside your printer. And if you look in the industry, I would say most of the time your company has one or few printers of one specific technology, so you will not have that much choice about the application. But yeah, in my opinion, first you set the process and then you start designing for this process. I don't know if everybody agrees, but
maybe I'd like to answer this question. From Hiricoiu, I think it's a very interesting discussion. So for me, it depends very much about whether you're looking at the part as a functional critical component, or is this part actually meant to be just for aesthetic, cosmetic performance. So if it's something that's going to be critical, then I think material properties are going to be really important, especially not just for medical, but for aerospace. You have to see the material property, then link to the design. That's my perspective. But if it's not for critical parts, then maybe the design or the aesthetic becomes more important than the material. So it very much depends on where you're looking about. It also obviously depends on the resources that you have. You can have more flexibility in the design, but less flexibility in the choice of material, because it's linked to cost. It's also linked to availability of the material, also linked to other constraints. There's lots of different things to think about.
Yeah, thank you. Actually, Eujin, there is a question that is for you in the chat. I have noticed. Thanks, Alexander, for warning me. It's from Antonio. He says porosity is one of the most important limitations of AM parts. So which actions in designing can be done for avoiding it? So
I think Antonio's question would be more relevant to particle bead fusion, especially for porosity, which could be more, I would say, encountered. But actually, porosity can also be encountered in other types of additive manufacturing processes, such as layer object machining or manufacturing. Or you have sheets of materials being stacked, and if you don't stack it properly or compress properly, you find that you have trapped bubbles. But I think porosity is mainly seen or documented in powder bead fusion, in particular depending on the spherical what we call shape of the powders, and that can be avoided if you have better sieving, and also in terms of the laser, if you have a good hatching pattern or a good control of the lasers, you can reduce the porosity. But there are also a lot of parameters. Can be down to the environment, it can be down to the splatter, it can be down to maybe if you recycle too much of the powders. Maybe Georg might know that much more, because I think Fraunhofer, you do a lot of research on powder bead fusion. Georg, you have anything to add to advise about how to reduce porosity?
Yeah, George. Okay.
Okay.
Maybe I would like to say something about this issue. Rather than avoiding the porosity, there are post-processes or supplementary processes that helps you to eliminate the porosities, such as hot isostatic pressing. Normally, hot isostatic pressing is a main production method for PM parts, has been used as a main production method for PM parts, powder metallurgy parts, in big parts such as the shafts of nuclear plants, etc. But nowadays, it has also been used for AM parts, so that under high temperature and pressure, you get rid of all the porosities in the part, but also then you have the risk of shrinkage that you have to balance. This is also another subject of research in the field of additive manufacturing nowadays. That's what I can say. Okay, I think we have some more minutes. As I said, if you have questions, you can raise your hand. You can ask through the chat. Maybe I have one question to Alexander that is my own question. Okay, so in case of changing a current design for a part that is manufacturing, that has being already manufactured with conventional methods, that is a cast part or a machine part, and you want to change it to AM, would you recommend to use the current design and modify it a little bit, or would you recommend to redesign the part from zero?
Thank you for this question. I think here there are two scenario cases. The one where your boss is actually taking a part or a component and is asking you to enhance the performances of this component, and it doesn't matter the way you're going to produce it. And in which case, I would recommend, of course, to completely redesign this part, or sometimes even as we've seen it for the antenna component, the whole assembly, and to rethink your product through additive manufacturing, because it's not always easy to, I would say, produce components that were traditionally produced with standard processes. We have seen, for example, Dr. Georg Schlick that presented this gear. Right, it won't be possible to produce it as it is, the full gear that is about 6 kilograms or 1 kilogram. I think it won't be able to produce it through additive manufacturing, because the center of it is way too thick, and it's going to create too much distortion, and probably it will lead to build failure. So redesigning those components is vital. However, there are components or some applications you won't be authorized to redesign them. For example, the spare parts on demand, we can think about old components that are required in nuclear power plants, which is not, we do not have the plants today anymore, but we need to replace those components in the actual power plants. You need to do it in the same way as they were done before, and not changing the original design. So I think those are the two type of applications.
Okay, thank you. Before, I think we are almost close to the edge, I would like to read a comment from our project manager, Adelaide, in the chat. She's saying that upcoming training will be available through the SAM project, focusing on design for polymers. These concepts will be approached to, I mean, the design of additive manufacturing. To follow all these events and the exact dates, please have an eye on the project website, www.skillsforam.eu. You can see it in the chat. Also, it is written on the bottom left corner on the slide on screen. Okay, so I would like to thank everyone for joining the seminar, and I hope that this session has been really fruitful for you. You will receive a thank you email with a satisfaction survey, and we would greatly appreciate if you share with us your opinion to make our events better tailored to the audience needs. As I mentioned at the beginning of this webinar, please follow us from social media, from the project website. Our next and third seminar will be held on 27th of April. It will be rather in a kind of panel format. It will be dedicated to young AM professionals and students, as well as we will host young experts and managers in AM industry to learn about their educational background, their opinions on positive and negative aspects working in the field of AM, the trouble they have faced, and many other issues. So I forgot to mention the topic. The topic of our third seminar is young experts and managers in AM. So please follow us from LinkedIn, let's say social or other social media tools, and the project websites to get informed and to join this event. So we hope to see you back there again as the project team of SAM. Until then, have a great day. Thank you very much for joining. Bye-bye.
Thank you all. Bye.